Okay, well, we kick off. So good afternoon, everyone. I'm Dan Kilper. I'm the director of the Connect Center, and I'm pleased to welcome you to our webinar this afternoon. For those unfamiliar with Connect, let me start by saying that there's really three areas that are fundamental to us. First off, collaboration is at the core of Connect. So we work with over 50 companies, communities, universities, and other organizations on research, development, and project work. And secondly, we shape the future of communications, right? Our research today is looking at today's 5G networks and then also looking ahead to 6G networks and driving advances in how people and things connect. We're headquartered at Trinity College Dublin, and we bring together expertise from 12 partner institutions across Ireland. We're funded by Research Ireland, and we innovate with a purpose, right? So our mission is to design communication technologies that are not only cutting edge, but also sustainable and beneficial to society. So that brings us to today's webinar, which is part of our Sustainable Future Networks program. And it's a series that will bring together researchers, experts from industry and other communities to explore how we design and deploy the next generation of communication networks and digital infrastructure, and also to explore how it might be made more sustainable and resilient for the future. So I'm delighted to open today's first session, which will highlight the Efficient Confluent Edge Networks project. This is a Smart Network Systems joint undertaking project funded by the European Commission. And it's pioneering the development of what we refer to as confluent edge networks, which is creating a confluence of radio and optical transport that will help us better prepare for 6G networks and address the challenge of densifying networks at the edge and providing resilient mesh connectivity. We'll explore this work in more detail and have an excellent panel of speakers, each bringing unique perspectives to the project. The speakers will present for a few minutes, and then once they're finished, we'll open the floor to questions. So I encourage everyone in the audience to think about questions, and please post them in the chat as they come, and then we'll gather those at the end and have some open Q&A and take your questions. So with that, I'd like to introduce the different speakers that we have today before we get started. So first off, we have Professor Paolo Monti from Chalmers University of Technology. He is the project coordinator for the ECO-eNET project and head of optical networks unit at Chalmers University of Technology. And his expertise covers energy efficient, resilient, and programmable optical networks. And he's led major international projects across Europe, the US, and Asia. He's going to outline the intuition and challenges behind the ECO-eNET project. Our second speaker will be Marco Ruffini, Professor Marco Ruffini from Trinity College Dublin. He's also a key PI within the ECO-eNET project. He leads the optical and radio network architecture group, and his work spans 5G optical networks, network convergence, and quantum networking. So he's going to discuss optical spectrum as a service and the coexistence of digital and analog technologies for more efficient networks. And then we have Dr. Devika Dass, who's a research fellow at Trinity College Dublin and a member of the ECO-eNET team. Her research focuses on advanced modulation formats, silicon photonics, and photonic millimeter wave generation. And she'll expand on this concept of optical spectrum as a service and explore this hybrid digital analog approaches and how they can support more sustainable optical access and interconnects. And then we have Michael Wallace, who comes to us from Embryonics, which is a company that's located here in Ireland, and they're rapidly growing, really making a name for themselves in terrestrial, airborne, and space communications. And he's going to talk about their research within the ECO-eNET project as well, and what they're doing in free space optical communications. Okay, with that, I'm delighted to hand over to our first speaker, Professor Paolo Monti.
Thanks a lot, Dan, for the introduction. I hope everybody can hear me well. I'm also going to share my screen. Here it is. Yes, hopefully everything is okay from your side. You can see
Looks good,
everything?
yeah.
Okay, great. So thanks a lot, as I was saying then, for the introduction. Very nice of you, very nice words. As Dan was saying, the idea for my brief talk today is just to provide maybe some general information about the project, more importantly, the intuition that actually pushed us to think about this new concept of confluent edge networks. First of all, who are the partners working in this ECO-eNET project? Well, you have a list here. We have a very nice consortium that puts together academic partners, operators, system vendor, integrators, and SMEs. But maybe let's jump directly into the intuition. So why confluence? Why do we think that we're going to need for 6G network this idea of a mesh on demand? And I have here a figure that was taken from the Future Networks Roadmap. This is not exactly the specific scenario that is addressed in the project, but it is basically where we draw our intuition from. And basically the idea here is that we know, and we are already witnessing today, the fact that we are actually shifting paradigm from having a backbone in our access network that was mainly due for legacy broadband services to something that is to something more, what we call here maybe the AI backbone. And what does that mean in practice? Well, it means that we know or we witness already a scenario in which we used to have data centers only at the edge of the access, more in the metro and in the core part of the network. But now these compute capabilities are moving more and more into our access network, very close to the end user. One reason for baseband processing, for latency constrained services, but the other is basically pushed by the need of processing AI. Whether it is just for regular services or what are becoming the day-to-day operation when we want to rely on some kind of support of artificial intelligence, and even more in the near-term and long-term future, where AI as a service or agentic AI kind of application would be part of our everyday lives. So compute nodes that might be more or less powerful, very close to the user, means also that the legacy north-south type of traffic that we had in the access will most probably move to something more close to a east-west type of traffic. But the legacy infrastructure is mostly tree-based. Think about passive optical networks, for example. On the other hand, with east-west traffic, we're going to need most probably a mesh. And how do we build this mesh? Well, we know that fiber from one side is probably the best type of technology that we can have, but on the other hand, it's very expensive to put fiber everywhere, and that's where we come in. So with new capabilities that terahertz and free space optic can provide, our idea will be that then we can combine fiber technology and this high capacity wireless technology and build a mesh that can operate on demand, that can provide low latency, high capacity, and at the same time can be energy optimized. Without going too much in the details, but I have an example here, for example, of what I mean of having a mesh on demand. You can see here, let me see if I can put my pointer. You have here a very simple example where we have some massive MIMO clusters that are operating, service their own users, and then they are basically backhauled to their BBU processing nodes, and all these nodes in our access are connected to different type of technology. You can have regular WDM, you can have optical spectrum as a service technology. And then what can happen in this type of network is that, at some point in time, maybe there is a need to coordinate these two different massive MIMO cluster, meaning, for example, that I have a high capacity, I have a peak in the number of users, and then maybe there is some interference to be managed. So it means that then maybe this cluster needs to be coordinated among themselves. So it means that maybe we need to move some of the processing capabilities that were running locally to maybe some aggregation node in order to enable this type of coordination. But we might not have a fiber there, or maybe the path or the combination of technology to go to that particular node might not fulfill the latency constraints. So if we have now this high capacity wireless technology that can be activated on demand, we actually can put down link on demand. And maybe we can also compose this different technology in a way that we can provide maybe some redundancy path if some enhanced reliability is needed. So now you know a little bit about where are we coming from, what's the intuition, and then what I have here in this slide is what are the tools that we're going to play with. So what are the technologies that we built our kind of work on? I already mentioned that we trust or we know, I mean, we rely on the fact that, you know, both terahertz links and free space optics will get to a point where we'll actually be able to have 1 terabit of traffic over capacity over 1 kilometer. And we will also be able to actually combine these two technology in order to maybe counteract some atmospheric effects. I already mentioned optical spectrum as a service as a way, you know, to reutilize part of the existing spectrum or infrastructure that an operator has and might not always be able to use. We need also, in order to operate our mesh on demand in a smart way, maybe we need to also to understand what is the actual situation in which the mesh in. So we need to do some kind of sensing, and we have some fiber sensing solution in this project. And of course, then we need to do control and management in a smart way in order to operate on demand this mesh infrastructure. But since this workshop is more, I mean, it's focusing also on some sustainability effect. So maybe let me highlight how this key technology can help also from the sustainability point of view. So we are targeting for our high capacity wireless technology also a very low per hour per bit value. And I guess our colleagues from Embryonics will talk more about this. If we have then optical spectrum as a service and this fiber sensing solution that we're going to propose, we will be able also to reutilize existing device in the network, for example, in the case of optical spectrum as a service, or we will be able also to do some monitoring solution that don't require the addition of extra devices. So also from a kind of already CapEx point of view, we're going to have the advantages. And then if we have this smart solution for the orchestration, we also can implement energy efficient operation. So I just have maybe a couple of minutes more, no more than that. I would like just to show you maybe already some benefits, especially from maybe the cost and the energy efficiency point of view, that this combination between, this interaction between mobile network and on-demand confluent transport can bring. So what you see here is, an example that is related to the integrated access backhaul, by which, in a mobile network, we can reuse some of the bandwidth that normally is used to serve a mobile user to actually do backhaul. And what we study is what is the effect in terms of benefits in terms of service coverage probability in a network when instead of using integrated access backhaul, we can combine that concept we just connect with fiber our base station. And as you can see, and maybe also our intuition suggests, the more base station we connect with fiber, so the more we offload the integrated access backhaul base station, the higher is the service probability that we can provide to our user. So there is a benefit already to bring fiber-like capacity to the end user. And there are also cost-efficient way to do that, right? As I said, we can connect everything by fiber, of course, but if instead of just connecting everything by fiber, we selectively replace some of this fiber connection with FSO that we know will be able to produce this terabit per second over a kilometer capacity, there are also indeed cost benefits. So you see that, for example, we can reduce the cost by many folds. And at the same time, if we can offload the integrated access backhaul operation using fiber by connected base station with fiber, we also have a better energy efficiency because then we reduce the interference for our end users, and we need less power, less launch power in our base station in order to serve those users. So this was first introduction of the concept of ECO-eNET and first benefits that confluent transport can bring. And then I'm going to now leave the floor to my colleague Marco that will talk more about optical spectrum as a service.
Thanks, Paolo. Thanks, everyone. Okay, so I want to start by just mentioning that ECO-eNET is about sustainability, and when you look at sustainability, there are really there's a number of things, but the first thing that comes in mind is energy consumption, for example. How do you make your system sustained? But it goes beyond that. Okay, I mean, of course, energy consumption is important because what we have seen is that traffic is growing fast, and the issue is that the energy consumed by the traffic as it grows is higher than the energy reduction that common technology, like going to a different nanometers size processor and so on, can bring. So this means that the whole thing will become unsustainable. But beyond the energy itself, there's also a lack of resources. Okay, so if we start using more capacity, of course we're going to run out of spectrum, and we're going to run out of existing fiber, which means then we have to deploy new fiber. So it's an idea that has to come up together. Of course, how can you go about this? I mean, some things, you would be surprised how some things that seems very sensible are actually not yet really applied in networks. For example, if you were home, you want to save energy, you turn off the lights when you're not in the room. But however, that's not the way telecommunication works. Although there is some research trying to go towards that direction. And again, one thing is you turn off to save electricity, but even more important is you want to turn things off when are not fully in use or in low usage, so that you can reuse resources. And this is important because yeah, I mean, it's important because again, if the resources are used all the time, then when you need more resources even for a short time, they are not available. Now here is where the concept of spectrum as a service comes in. So spectrum as a service, the basic idea is that if there is a fiber, the fiber might not be fully used. So you might let a third party use part of the fiber. Now that's not really what happens at the moment. At the moment, the fiber belongs to an operator. Of course, the operator, if it needs more capacity, would add transceivers and so on, and might be selling some capacity, but it doesn't leave third party the flexibility to use part of the fiber as it was just part of their own system. With spectrum as a service, that implies two things. First of all, opening up part of the fiber so that it can be used, but then as a consequence, make the system a lot more dynamic in terms on how the channels are being used. And again, that's something that today is not really happening for a number of technological reasons. So there are limitations, for example, when you want to be dynamic in a network on things that could happen because you don't know exactly how the system will behave. And that's, again, that's one of the main limitations. However, what we've seen that we are addressing this through ECO-eNET, and in general, we have seen that there is a much increased use of artificial intelligence in network control, and the use of artificial intelligence is really across this for this reason, to really help make the network more dynamic. And how does AI does this? Well, for one, AI can build models, what we call digital twins. So you can build a digital twin of a model so that now in advance what's going to happen with quite a good degree of precision, what could happen to your network. So you can tweak and you can prepare things in advance to the point where you're kind of confident that whatever you're going to do is not going to disrupt the network. And this is crucial because if you don't know what the network is going to happen, then the operator will never open it. And then on the other side, once you know this, and the system is automated, you can actually start automating the decision making. And this is where there's a lot of work converging in this. And again, the ECO-eNET is really working towards this part. And I'm gonna now go to the next speaker.
Yes, so we'll hand off to Dr. Devika Das, who's going to give us a little bit more details around some of these technologies that you just mentioned. And I'll remind folks, if you have a question, instead of raising your hand, please put your questions into the chat, and then we'll take those questions at the end. And then also you can raise hands at the end of the overall presentations, and we can have some conversations then. So we'll move on to Devika, please.
Good afternoon, everyone. I'm Devika Das, and today I will present our work on confluent analog digital networks and how can we support future dense deployments in a cost-effective, energy-efficient way. So the next generation networks will require far more devices and users per square kilometer. And as the user density grows, the network deployment will become denser with many more much smaller cell sites. And with the increase in the cell sites, there would be higher capacity demands, as well as providing this higher capacity demands in a cost-effective way is a crucial point, which can be served by shifting to millimeter wave and terahertz frequencies. So we can employ the higher frequency carriers by using RF upconversion, which uses RF devices. However, they are very expensive, and an alternate to those would be using a technique called optical heterodyning. And in optical heterodyning, the optical carriers can be generated using they can be generated using the photonic integrated approaches. And it can be either a hybrid integrated dual laser module or a silicon photonic optical frequency comb. And in optical heterodyning, these sources generates two optical carriers, which are at a frequency separation, which is the desired RF carrier that we want. So when the two optical signals reach at the photodetector, the photomixing causes a generation of electrical RF signal at the same frequency as the separation of the two optical carriers. So with this technique, we do not have to use the expensive RF devices for generation of millimeter wave or sub-terahertz RF carriers. And further moving on, the next generation networks would require higher energy efficiency and higher spectral efficiency, which can be facilitated if by centralizing the resources of the radio access network. So having all the processing at the central office and have simple radio units at the antenna site, because the denser cells means more number of RUs, and as we increase the number of RUs, we do not want the RUs to be very expensive. So in order to simplify the RUs, we use analog radio over fiber technology, which has more spectral efficiency as the digital radio over fiber technology, because in digital radio over fiber technology, the baseband is transmitted over the fiber. And as you can see in the diagram, that at the antenna side, it requires a lot of processing like optical to electrical conversion, digital to analog, and RF up conversions. But we can reduce this complexity of the DU and RU at the antenna side by moving the DU towards the central office and co-locating it with the central unit. So we see that we can further reduce this complexity by sending the RF signal over the fiber instead of sending the baseband. And at the antenna side, the simplified RUs would be way more cost effective, and this leads to scalability and sustainability of the networks. So we have shown the coexistence of wireless and optical networks by employing all these different technologies, and we have shown the transmission of the optical spectrum as a service signal, where we have used one of the nodes in the ECO-eNET, which is a metro network in Dublin City, and it connects different higher education institutes across Dublin. And at the TCD, at Trinity College Dublin, there are two nodes or two ROADM nodes. And at one node, we have emulated a central office that creates the OSAS spectrum, which consists of the digital coherent channels as well as the optical heterodyne millimeter wave and sub-terahertz signals. And we have transmitted these signal over the ECO network. and received at the edge node that is again placed in Trinity College Dublin. And this edge node provides the signal to different types of services, which includes the wireless and optical technologies. And in the end, we were able to show a terabit scale coherent transmission, as well as millimeter wave and sub-terahertz signals were carrying 6 gigabits per second and 4 gigabits per second data rates. So in the end, I would like to say that our results show the combining of optical heterodyning and centralized RAN with AROF can enable delivery of high capacity while keeping RU cost and complexity low. And this is a promising path to sustainable confluent optical and wireless networks. Thank you for listening to me.
Thanks, Devika. Okay, so now we'll go on to our last panelist. So this will be Michael Wallace from Embryonics. Michael? Okay.
Yeah, I'll just share my screen. You can see my slides?
Yes, yes.
Yeah. So just, I guess, a bit about Embryonics. We're a company based in Galway, kind of a startup at this point, probably scale up. And we are essentially developing optical terminals for various different applications, but mainly focused on optical comms in space. So for the ECO-eNET project, our role is to develop these free space optical links. What is a free space optical link? It's simply a link that, rather than using a fiber, you're transmitting your light through free space. You can see this image here is an image I took from a group who demonstrated this all the way back in 2001, I think, using LEDs. Pretty low speed compared to what we're trying to do nowadays, but it kind of demonstrates the concept. You're just shining light from one building to another. So kind of what's the motivation behind trying to implement these types of links? There's plenty of reasons I've kind of highlighted four here, and in green I kind of highlight the ones which I think maybe are related to the kind of eco aspect of this project. So rapid development, rapid and flexible deployment. All you really need is a building or a mast that you can put your optical terminal on, and you're kind of in principle good to go. You can set up a 1 terabit node without much difficulty. So that would allow the people designing the networks to design them without considering how difficult it is to deploy fiber here. So I think it opens up a lot of possibilities. Lower upfront cost, obviously, if you're not tearing up pavements to lay fiber, stuff like that. No spectrum licensing. This is all in kind of the C-band or O-band typically, or well, in this case it's red. But you don't need to license millimeter wave spectrum. And as I kind of touched on, no physical disturbance and easy deployment. So in ECO-eNET, we're focusing on terrestrial links, so kind of point to point from one building to another maybe. But there are a whole range of other kind of applications which are kind of highlighted in this image here. So we actually also work a lot on satellite to satellite links, satellite to ground links. There's even projects where you have, maybe a plane or some flying object which you want to communicate to. And there's even stuff going on in kind of deep space optical comms. And the kind of hardware we're developing in ECO-eNET also feeds into a lot of these other applications as well. So I suppose, why isn't everyone using FSO links already? The main problem is, well, I guess in space there's no atmosphere, so there actually are already people using these links, SpaceX, for example. But once you're not in space, you have atmosphere, and that results in essentially the kind of disturbance of your light as it travels through the atmosphere. So these are kind of images actually taken years ago by one of the founders of the company in her PhD. I think a link across Galway, and you can see, I mean, this image here is just, you're seeing kind of the laser light reaching the receiver, but as a function of time, you're basically going to get this light being disturbed, and you get different types of errors kind of caused by those aberrations. And this kind of plot down here on the left is the typical field pattern you might see when you focus your beam down. So why is that a problem? Well, at low speeds, it's not such a huge issue because you can just detect it with a photodiode. For high speed, kind of 1 terabyte links, you need to couple this light into a single mode fiber, and you can't do that really efficiently with an intensity pattern like this. You're going to lose a lot of your light, and you're going to lose a lot of your light as a function of time. It's basically going to drop in and out as that kind of turbulence changes. This problem has kind of been solved already in astronomy. You see these pictures a lot where they're kind of shining a laser into the sky. What they're actually doing here is kind of creating what's called a guide star, which they then measure, and they're actually able to counteract all of these phase aberrations, and they can very effectively essentially remove all those aberrations, so they get back to the original point spread function that was sent. The only problem is this is, you know, developed by astronomers. It's all low volume. They don't care about energy efficiency, scalability, any of that stuff. So it uses kind of bulk optics, very expensive, bulky, not very energy efficient. So what the challenge is to kind of make this commercially viable, basically. So how are we doing that? Well, we are taking a photonic integrated approach. So we are developing hardware in the form of photonic integrated circuits. So for anyone who doesn't know what a photonic integrated circuit is, it is, if you kind of think of how electrical integrated circuits kind of took lumped, you know, resistors, inductors, transistors, and integrated them onto a small silicon chip that you might have in your phone. Photonic integration does something similar with bulk optical components. So this is like a traditional adaptive optic system. And it's using kind of similar semiconductor processing methods to integrate those onto a single die or multiple dies, depending on your configuration. So that's the kind of challenge we've set for ourselves, is to integrate something like this onto a couple of photonic integrated circuits. And then the functionality of that will basically be to take that kind of aberrated light, which is very difficult to couple into a single mode fiber, and couple that very efficiently into a single mode fiber. So that is, it's essentially reproducing what a traditional AO system would do. This is kind of what those photonic integrated circuits will kind of be integrated into the system. So it'll be this kind of component here, possibly connected to multi-mode fiber or something like that. And then that will all be integrated into and this is further down the line, but integrated into an optical terminal that can be put on a mast. And it has an aperture and a lens which will focus it down onto this device here. and this essentially will be compatible with existing off-the-shelf commercial transceivers. So it's just something you basically plug into a existing transceiver, and then you can transmit that light and receive it over free space. So yeah, that's kind of what we're working on. The current stage of the project is we are essentially designed, fabricated, packaged. The only thing we don't really do is fabrication. So the foundries do that for us. We submit our designs. And so we're moving on to kind of testing our system in the lab, proving it out. So yeah, that's my slides.
Great, thanks, Michael. Actually, I just well, first off, it's really exciting what you guys are doing at Embryonics and the space communications, and now bringing it to terrestrial and making it scalable. And there's the obvious question that people are going to wonder about. So are we going to have to worry about a bunch of laser beams bouncing around and getting into our eyes as we're trying to use these things in the terrestrial networks? Can you maybe comment on that a little bit?
Well, probably not is my answer. There are regulations and stuff on how much power you can transmit in free space. So we'll be adhering to them. But also 1550 is very kind of safe. That's 1550 nanometers is the wavelength we would typically operate at, which your eye basically absorbs almost everything. I mean, before it hits the retina, you've basically absorbed everything. So it's a pretty low risk wavelength to operate at.
Great. All right, thanks. So, well, first off, if folks have other general questions and things, please you put it in the chat, or at this point, raise your hand and we'll take some questions. So I want to talk about densification is a major challenge. It kind of started with 5G. People talk about densification. A lot of network operators are struggling to get more access points out there so that we can have better coverage and capacity. But they're running into challenges of cost and energy and these sorts of things. So if we're creating a mesh network, doesn't that make it harder? How are we getting more energy efficient, and how is this going to scale and cost if we're creating mesh networks at the edge? Maybe let's start with Paolo, and others can jump in.
Okay, then I can start to try to answer this. So as I was saying in the short introductory talk that I had, I think the key here is, I mean, of course you're right. I mean, if you wanna have this mesh at the edge, of course we need some extra equipment for sure. But I mean, that's also, as Marco was saying, I mean, that's a consequence of the high capacity and I mean the evolution of services that we have to service. So in some sense, from that respect, there is no way out. But having the possibility to actually operate dynamically this infrastructure and actually deploy or turn on and off resources when needed, I guess that helps a lot in order to have a more efficient, energy efficient, but in general a more efficient type of operation. I can make an example as an example the interaction between the mobile network and the transport network that this confluent idea that we have can help, right? Mm-hmm. So we need to find ways to operate efficiently our cell-free massive MIMO clusters. But so far today, this is done basically by just looking at the mobile network situation or conditions. Knowing more about the transport, so knowing maybe where extra capacity can be leveraged in order to get to a compute node, or even better, knowing more about the end-to-end budget, whether it is an energy budget or whether it is a latency budget, can help us compose the resources that we're going to assign to that service better. So maybe I don't need a very dense or a very high power transmission to my end user. If, for example, I know that I can rely on some, leftover capacity or leftover latency that I can get from my transport, right? So I think that there are a lot of nice trade-offs that we can exploit here the moment we put the two worlds together and we add the dynamicity on top.
Great, thanks. And Marco, maybe you were commenting on that. And actually, Marco, I know that you're doing some interesting work and thinking about how we use renewable energy. So how might this also factor in if we're thinking about renewable energy?
Yeah. So, I mean, the first thing I think is to notice that, we're not building a mesh network to, just because it's an idea that we come up with, or we're building edge clouds. I mean, everyone is building edge clouds, and the reason is because they are required, and it's the same concept of AI, because a lot of time we're looking at using AI for energy efficiency, and the first question is, sorry, is not AI consuming more energy? So why, what's the point of the energy efficiency? And I think the reason is the same, is both with edge cloud and AI, they are coming, they're in there. Then it doesn't matter whether, it's about energy efficiency or not, they are going to be in there. So the question becomes, how do we make mesh network and the AI more energy efficient? And that's the thing. And what this project do is, trying to make, we hear of a concept like AI native, for example. I think ECO-eNET, we want to make the network mesh native, if you want. So it's not mesh because we add links afterwards in a way that try to put patches across the network, but it's about how do you design it? And if you design a high performance network, it is going to be a mesh. But from the beginning, it's not going to be a ring. So it's about the design, and I think that's what we want to do. Sorry, the question, Dan, can you repeat? I got lost.
So renewable energy. How does renewable energy factor in here?
Yeah, and then I mean, of course, there are. I mean, the thing about energy consumption is that is energy consumption bad by itself, or is it the consumption of fossil fuel energy that's a problem, right? And a lot of time it has been pointed out that if we had the limitless supply of energy, then it's not going to be such a bad idea. For maybe we'll get one day with fusion, nuclear fusion, and so on. But in the meantime, we do have other energies which are renewables. Okay, so we have wind energy, we have solar energy, and so on. Especially in Ireland, the wind energy is probably the biggest part. And the idea is that we don't control the wind, so the wind comes in when it comes in. However, we can predict it because it's based on it's weather dependent, and we can predict weather. So we've done studies with ESP where, for example, you can predict extremely well what your wind is going to be in the next 24 hours, and reasonably well, which still means above 90% accuracy when it's even 48 hours. So that means if I know in advance where energy is going to be, can I deploy, can I move around my load, right? If I have a data center, and again, today data center, I mean, they're physical entities, but they're all interconnected. Okay, so the load can move around data centers quite easily. So can I, move the load where maybe there is more energy, when there is more energy available, possibly also where there is more energy available, maybe, especially with the use of battery, if you cannot really postpone some of the processing. And I think this comes, this becomes important. But of course, as I said before, this requires flexibility. And flexibility on the compute, of course, is the first thing, but flexibility in networks, because the only way I can move data around in such a short time and a huge amount of data is really by having a network that's dynamic, that creates links in a certain direction where they're needed, then removes them so that the same transceivers can be used in a different direction. Right? So I think that's really what we're looking at here.
Great, thanks. And I think in building that mesh, right, one of the challenges, and I think network operators today are really facing this, is as they try to densify and reach more access points, it's hard to get fiber everywhere. I mean, fiber gives you great capacity, and if you can get it there, fantastic. But we really need wireless capabilities to be able to do that. And I think that's where this free space optics comes in. Now, Michael, maybe you can talk about, I mean, you still, with free space optics, what happens if a bus drives through your beam or a bird flies through? Are we going to lose connectivity? Can we combine it with other radio technologies? And what are you doing in the project to kind of address this challenge?
Yeah, so I think, I suppose the radio and the optical kind of complement each other. I think the main, well, one of the things which would cause you to lose your optical signal is kind of fog. But for the RF signal, as I understand, that's not an issue. So, and then conversely, for RF, heavy rain, I think could block your signal, but that's not so much an issue for the optical. In terms of kind of like transient signal outages, like maybe a bird or something, there is a lot of work ongoing as well, looking into how you either recover from a loss of signal, or there's different kind of ways you can encode your data by like overlapping kind of different bit sequences and all this kind of advanced error handling, so that even if you have dropouts, your signal isn't totally lost. The data can be recovered. One thing to say about it is that, I mean, what we're aiming to do is to minimize as much as possible the amount of signal outage we get, but we still expect that we will have some fades in the signal where we will, for maybe a millisecond or so, we'll lose our signal. So we are working on various ways to kind of overcome that. And I think a lot of that, there's already a lot of kind of track record in RF communications. A lot of those problems are to a large degree already solved, so it's kind of a challenge of porting those over to the free space optics solution.
And I guess both, when you need high capacity for both the free space optics that it brings you to, if we're densifying in this way, but also if you're talking about terahertz or sub-terahertz, as Devika was talking about, right? And that's where, if you have a dynamic mesh at the edge, you can dynamically respond to these different light of sight perturbations, and you can hand off between the optical and the wireless, and also move around to different access points. Yeah, so that's another, I guess, asset of this mesh approach that's being looked at in this project. Yeah. Yeah,
exactly.
And then Devika, so then you need to be able to handle these types of signals. So you're looking at sub-terahertz in the fiber together with these digital coherent, really high capacity signals, right? And did I see right? So then you showed a spectrum, so that's optical frequency and power on the vertical axis, and these digital signals look like big fat very wide signals in the spectrum, taking up a lot of spectrum, but those skinny little slivers, those were the sub-terahertz, is that right?
Yeah, so it's basically the digital coherent signals are QAM signals, which are like occupy more spectrum, whereas the analog radio over fiber signals, so the millimeter wave and sub-terahertz signals on the spectrum, they are compressed multi-carrier signals, which each carrier has multiple, each carrier carrying QAM signals, and they are like orthogonally arranged, so they occupy less spectrum. And so the idea is basically, if there is a metro network which is transmitting big coherent signals, we try to put the analog radio over fiber signal, we try to squeeze them in so that they do not interfere with the digital coherent channels, but also we use the small parts of the spectrum that is not being used to transmit some information. And with analog radio over fiber, it doesn't require much spectrum, so it can actually get into those empty spaces on the spectrum and deliver more data as compared to a baseband signal.
Right. And so you're really becoming more spectrally efficient with these analog signals being combined with the digital. Is that correct? Yeah.
Yes, so it's like complete use of the spectrum. We are not wasting any spectrum, and also transmitting different types of signals like the analog and digital together.
And so we have one question here about how does this confluence of optical and wireless enable energy efficiency improvements. I guess if you're able to do this radio over fiber, does that allow you to improve the efficiency of how you're processing these radio signals?
Yeah, so as I showed in the slides, if we use analog radio over fiber with centralized radio access networks, the radio units, multiple radio units are connected to a single central office, which has a resource pool. So it's easier to scale the network and add more radio units, which are simpler. And also it's cost effective because all the radio unit cost effective because radio units are simpler, and energy efficient because each radio unit will be sharing the resources with the other radio units in one cell site. So that's how the energy efficiency increases. So sometimes when the radio unit is not being used, the resources can be allocated to the other RUs.
Okay, very interesting. And there's the densification of the kind of traditional cells, but then also as you densify, you start to get interference on the wireless side. I think that leads to some of the interest in these cell-free approaches. And maybe I'll ask Paolo, you guys have been looking at these kind of cell-free approaches. How does that factor in here with this, both the mesh and then also this integration of the optical and wireless together?
I would say that, yeah, it relates back to what I was mentioning before on the benefits of actually having the possibility to play with both technology domains. So when you have a cell-free massive MIMO cluster, you need to operate it. You need to decide how big is that cluster, how you need to be able to manage interference maybe with other cluster. And at the end of the day, this also means having to select what is your cluster head, where your process traffic needs to go, maybe towards the mobile core. If you need to manage interference, means that your termination point maybe needs to be in some common nodes into the network. And then, as we were saying before, this means that you need to have capacity to get to those places. You need to be able to measure or to manage the latency over which, that you need to enforce in order to do this processing. And then again, you can play with that, right? So if you don't have the capacity to get to a specific processing point that has the capacity that you need, you may create it on demand, right? So you can instantiate one of these wireless, high capacity wireless link. Or vice versa, if you know that you cannot get to a good processing point, so maybe your end-to-end latency constraint might be affected, then you decide to do something different on the mobile part, right? So maybe then you operate your cluster differently or you structure it differently. So again, it is more a matter of knowing what are your current capabilities in your specific technology domain and mixing it up and optimize together with the transport, I would say.
Great, thanks. And one more thing I want to touch on before we wrap up here. So there's mention with optical spectrum as a service, actually integrating sensing with the communications in the fiber, right? And Marco, you're doing a lot with sensing. Maybe you can comment. What's the interest in sensing, and why is it such a interesting topic that we're hearing so much about today?
Yeah, thanks, Son. So, the interesting thing, first of all, of spectrum as a service is that, we hear a lot about it now, but it's been there for like 20, 25 years. The big difference is that this has been there as a bespoke type of activity. For example, if I want to see temperature in an oil well, bringing electronics down is dangerous because it could create sparks, they break under pressure. While, doing it with fiber, it's a no-brainer. Same things, I've heard application where, if you want to see if your cement is, large pouring of cement is getting dry in the right place, and so on. So they've been there for many years. However, the commonality is that they work by sending signal over fiber. And now, people are starting to think, well, we have about, I think, 5 to 8 billion kilometers of fiber deployed around the world. And can just we use existing fiber as a sensor? And so on the follow-up of that, there's a lot of work that has come up. For example, how do I move from sensing on a very specific link to sensing on a link that belongs to a network, where maybe there is other channels and so on. And the application, there's a lot of applications. You could sense, for example, urban sensing. You might be willing to sense how are cars moving across certain roads, so that you might even optimize how the traffic light will work. You could sense for vicinity of drones, for example, if you are near an airport, and I think these are very common things that we are hearing today. Or else you can sense the temperature of the seabed, whether is it changing, is it affecting the sea life? There's a lot of things that can be sensed. And I mean, if you think about it, again, the one issue with sensing is that same thing is like like for a radio transmission that you do over fiber, you need fiber, and fiber is expensive. But the same way you could send this channel from your base station over fiber using spectrum as a service, you can also send an optical probing signal using spectrum as a service. So, I mean, spectrum as a service is really a very interesting way of just giving part of capacity, which is commonly available, across multiple fibers. And this is just a no-brainer, as in, this is just a specific economic advantage once it can be used properly. Okay, at the moment, I think we're still investigating the AI technology to make sure that the signal don't interact badly with each other. But it's a no-brainer because, the operator has spare capacity. So if there is not disadvantage in using it, that they can just make more money with the same fiber. And users is just going to be able to get capacity at much lower cost, because for an operator there isn't really a cost. It's just about giving part of the unused fiber for some time. So it's and again, sensing is, I see sensing just an additional application of what we're doing on spectrum as a service.
And here it's using that in this kind of edge mesh environment for greater resilience. You can use that sensing, that context awareness, and then adapt your mesh network in response to that.
Yeah, I mean, you can sense third-party features like temperature and so on. But of course, the first thing you can sense, if anything, is getting close to the fiber by definition. So if there is someone digging the road, for example, in a place that they're not aware, the fiber itself, by sensing vibration, will tell you actually, there's something coming pretty close to me, and you might be, you may be willing to examine it before it gets worse, something like that.
Okay, great. Okay, so we're just about out of time. So with that, we'll wrap up here. And actually, that's a great lead into our next installment of the Sustainable Future Networks webinar series. We'll talk about the ICON project, Intent and Context Aware Optical Networks, which is focusing on this integrated communication and sensing. So that'll be on October 22nd. So definitely tune in for that. But I'd like to conclude today and say thank you to all of our speakers, Paolo Monti, Marco Ruffini, Devika Dass, and of course, Michael Wallace, for sharing your valuable insights today. We heard about how the ECO-eNET project is tackling the challenges of future networks, helping us to densify and integrating the cell-free MIMO approach together with optical transport and exploring hybrid digital and analog communications to realize this edge network and edge mesh network. And special thanks to the audience for joining us today, and also for contributing some questions. If you'd like to learn more about the project, so we just had it posted in the chat there. You can see ECO-eNET.eu is the project website. So please check out the website. You can also sign up for a newsletter and follow the project on LinkedIn. And we've just shared a little bit of it with you today, and please go and learn more on the website. So thanks, and I hope you'll join us again for the next installment of our webinar series.
Great. Thanks for the organization.
Thank you. Bye.
Thank you.